Okay, cool. Thank you so much. It's wonderful being a local finally after so many years of just coming here and spending a day or two. It's really nice to actually be here permanently for now. Thank you, Alan and Jess and Jared for organizing. They did all the work. It was really nice to have that all taken care of. So thank you, and anyone else who contributed. So for this talk, I will be talking about the sedimentary response to diapirism in the Flinders Ranges. So I'll go over a bit of things that I worked on for my master's and PhD, but then also just more big picture things as well, and new research directions. So for this talk, I'm just going to emphasize how the Flinders Ranges, which I suppose I'm preaching to the choir in front of everyone here, but it's a unique and natural laboratory to test a lot of really amazing hypotheses and geologic models that we see in the subsurface on seismic reflection data. So the Flinders gives us a really unique opportunity to look at things in detail that we couldn't normally see on seismic data. I'll also be going over the economic significance, not necessarily the value of the Flinders itself, but again, an analog to all sorts of energy systems. Also, just a comment on integrated research and the importance of it. And then I'll be briefly going over an introduction to diapirism, salt tectonics, salt sediment interaction. Just there's a lot of jargon in this field, so just going over a bit of that. And then some new research ideas and key messages. All right, so one of the reasons why I personally love the Flinders Ranges and other salt basins that are exposed on the surface is that it's a natural laboratory to test controls on sedimentation. So when we talk about sedimentation patterns, generally in stratigraphy, we refer to two different types of cycles. Those first one being autocyclic. So that's something that happens very local in the sedimentary record. This can be something as simple as a delta lobe switching its location to a point bar meandering in a different direction. So it's a very local sedimentary pattern that is documented. And then we compare those against allocyclic signatures. So those are much bigger scale. So if you're familiar with sequence stratigraphy, it'll be on the order of like third, second, first order scales. And these are typically considered to be regional tectonics. So the type of basin that you're dealing with, eustatic sea level, and also climate cycles. In salt tectonics, or when you start including salt or evaporites that begin to move, it's very difficult to distinguish the difference between autocyclic and allocyclic cycles. And that is essentially going to be sort of the crux and what I'll be continuing to work on for this postdoc with Kathryn and others in this room. So this is a really cool image, and I actually purposely included it because I wanted to show it in relation to some of the talks that are coming up after mine. So this is a really cool image. This is northern Canada, and you can see here you actually have two salt diapirs that are cropping out, and you have sea ice sitting over here. So this could be somewhat similar to what we see during snowball Earth time. I just thought it was a really fantastic image. But yeah, I put that up there because it really emphasizes the need to understand local climates and also sedimentary input. So these would be the autocyclic patterns that we would be looking for in and around and near a diapir. And then also the allocyclic signatures would be the global climate, the basin type, and then the eustatic sea level. So I thought this was really interesting. Okay, so moving on to the resource sector. So in Australia specifically, and I'm sure everyone is well aware of this, there's a huge emphasis to unlock and understand the country's evaporite basins, and then also to use it not only for minerals, but hydrogen. And it's really important that we understand what we see in the Flinders Ranges, even though we wouldn't necessarily be storing hydrogen or exploring for minerals there. Again, it's a beautiful analog to understand how some of these systems form. So beyond just hydrogen, there's a whole suite of other economic significance for evaporites. So mainly in the past, and all of my funding and research was dominated by support from the oil industry, mostly based out of the US. But now there's been a complete diversification of understanding evaporites and salt tectonics and how it applies to other energy systems. So beyond just extracting petroleum, there's also an emphasis to understand the inside of diapir bodies for storing petroleum for like a national reserve if there's an energy crisis, nuclear waste repository, carbon dioxide can be stored, and also hydrogen. And then also historically, it was famous for mining sulfur, but also copper. And there's really been a rejuvenation of understanding how we can find those resources as well. And one thing that I'm working on in particular is taking learnings from like the petroleum industry, for example, and seeing how we can use some of those concepts and actually apply them to help us understand how to find minerals associated with salt diapirs. So there's a lot of things that it's slightly different spin, or you're looking for something slightly different, but you can take that knowledge from one of the resource sectors, repackage it, and then apply it to something else. So that's really important going forward. And just to note, I was a part of a special volume where we talked about these different sort of energy systems. It was through the AAPG. This is the volume right here, a two-part volume. And that's where we start to really try to incorporate a lot of papers from different energy fields to assist with the evolution of the field. All right, so now literature gaps within the Flinders Ranges. So historically, there's sort of been this siloed research between different research groups in different locations, different continents, things like that. And this is just kind of an example of where, in my mind, I kind of saw things sitting. But I'm hoping that as we continue to collaborate and move forward and work together, that all these different disciplines can start to come together, and we can start to work together to really make big advances in the overall science and understanding of this crucial part of Earth's history. And just another important note is the cultural and archaeology significance, and really starting to bring that in and those stakeholders in working with us more closely. So first of all, I'm just going to talk about broadly what is salt tectonics. So these are three key textbooks. This is not something that obviously is typically taught in an undergrad bachelor program. A lot of times most geos never learn anything about it. So it's really important that we continue to offer this in our education system. So let me this person. But broadly meaning salt tectonics encompasses any type of deformation involving salt or other types of evaporites. The term that we use is called halokinesis, and it's primarily driven by salt that upwells and then withdraws in other places. Not necessarily by regional tectonics, but can be enhanced by regional tectonics. And when you start talking to experts, they'll sit up here and probably argue for half an hour of that definition. So I'm not going to get into that, but just know that it's a whole nother integrated discipline within earth science. So now we'll be moving on to what is a salt diapir. So typically, if you look in any sort of intro textbook or Google salt diapir, you'll just see like a very classic like salt dome shape. That is actually really rare to see salt perfectly in that sort of Q-tip shape. It can look all different sizes and shapes. That's just one thing just to be aware of. When you start looking at the different diapiric bodies in the Flinders Ranges, you'll see those different shapes of the diapirs, and that's all because yes, shortening from the Delmirian orogeny, but it's also because they would have originally had all different sizes and shapes when they were forming and flowing up. Another key component to understanding salt tectonics is salt sediment interaction. So this is something that I really focused on, especially during my master's degree. And basically what a halokinetic sequence is the definition is right here. So it's an unconformity bound growth strata that's associated with passively rising salt diapirs. And depending on how fast the salt is rising up through the subsurface and the sedimentation patterns are being deposited, you'll get a different geometry or different shape of a stratigraphic unit that is up against a salt diapir. So we have, these are end members, so they can definitely have some variability between the two, but we have hooks and we have wedges. And when you start stacking those up, so these generally form at like the parasequence level, so between the 4th and 5th order. Once you start stacking those up, you can get something that sort of looks like this cartoon over here, or this cartoon over here. So examples of this so we have our models from this work sitting over in the bottom right-hand corner. This is what we see on seismic reflection data. This is an example from the Gulf of Mexico. And then here you can actually see a map that I co-authored from, this is the Pinda diapir and the north central Flinders Ranges. You can see all of these halokinetic sequences starting down here. This is the Wanaka group right up here, and the Bonnie, and then we go into the Ronsley, and you start to see all these folds and upturns in and around this salt diapir and this salt wing sitting right here. So it's really great to be able to not only characterize the structural geology, but also seeing the depositional environments change as you're really close to the salt body right here. They change as you go away from the salt body. So local facies variations. So these salt sediment interaction is very much of a local or an autocyclic process. It has depositional environment variability, typically on either side of a diapir. This is a very simple, kind of an older cartoon, but here you can see a salt diapir in the middle, and then it's very much, at least this example, it's very oversimplified, but it mimics like a classic sort of reef atoll system where you have a prograding shelf on one side, and then you have a back reef over on the other side with a steeper margin. So yeah, it's just really amazing, because what these diapirs would have created topographic relief that would allowed and would have enabled all these really beautiful different types of sedimentation patterns to take place. And this would have happened through the entire depositional system in the Flinders Ranges. So now we'll go to regional facies variations. And this, I think, is where, especially in the Flinders Ranges, there's a big gap. And when we start talking more in the regional scale, we'll shift from saying salt sediment interaction to salt tectonics. And this would be more of an allocyclic process. This is an example here of a big long seismic section going through the offshore Gulf of Mexico. So Texas would be over here to the north, and then Mexico would be way off in the distance down to the south. And basically, if you follow these colors, you can see how the thickness changes are really different as you go along strike, and it's all greatly enhanced by the salt tectonic movement. So yeah, and this, I think, is something that we haven't really tackled greatly. We know that there's thickness changes in the Flinders and beyond, but we haven't sort of incorporated how the salt is influencing those changes on the really broad regional scale. The next thing I'm going to talk about, so this is something I more worked on for my PhD, is understanding diapiric inclusions. These are bits and pieces of broken up rock that are inside of the salt diapir itself. I originally started studying this because I was drilling exploration wells for shale in the offshore Gulf of Mexico, and we would hit these things, and they're a massive safety risk. So that's kind of how this all got started. And then now it's more of a understanding where these things are located, so you can avoid them when you want to make a cavern to store hydrogen. And there's also really amazing copper deposits that are also associated with this. So now there's definitely more, it's like transforming the implications of understanding this. So basically, I've made an attempt to understand structurally and stratigraphically how the inside of a salt diapir behaves. I can tell you it's not straightforward at all. It's like pretty, it's like one of those things that you could probably spend a whole lifetime trying to understand, but I am working on just trying to come up with some really broad things and making a classification system that can actually be useful. So this is an example. I love this picture. This is from Iran, and you can see these beautiful sort of wiggle marks of the inclusions sitting inside of the salt. And when I say inclusions, I'm referring to a macroscopic piece of rock that's inside of a rock body The reason it's important to make a classification is in the literature, and depending on what company you work at, they'll have a different name for it. So there's all sorts of informal jargon that's all over. It's in reports, it's in literature, it's kind of everywhere. So there's definitely a need to kind of bring it all together. A key thing to note is that inclusions are things that are inside salt bodies, are not in their original depositional position, and they often you can't really see them on seismic that well. It may be mistaken for noise or just something else like a gas pocket or something like that. This is just an extension of those definitions. I'm not going to go into huge detail, but the reason why this is an interesting project in the Flinders especially is understanding the age of them. Because we don't really have biostratigraphic or very accurate chemostratigraphic control, it's always a mystery of what those rocks are that are sitting in the diapirs. They're really hard, some of them, to actually piece back and understand where they are in the regional stratigraphy. So here you can get inclusions from sort of every part of your basin. So you can have really old bits. Wolfgang had mentioned there was a piece of granite up in the Blindman diapir. So that would be considered an inclusion from the pre-salt. So that'd be like your basement rock in the blue. You can also get bits and pieces of your autochthonous salt. So that's sort of the main evaporite unit sitting at the bottom of a rift basin. You can get bits and pieces of that broken up and contorted up into a diapir. And then you can also get much younger sediments that are incorporated into salt bodies, and that happens when you have different salt bodies coalescing and coming together. So here are a whole suite of geologic models. So you can see here that there's all sorts of structural mechanisms that allow bits and pieces of basement rock to become incorporated in a salt body. Some structural geologists really like some of these, some of them really hate them. It's a whole wide spectrum of what we think is actually going on there. This is the hardest one to understand because we can't actually really see it happening per se. This is very much of a model, and you can't really even see this on seismic. This is something that you would like basically exclusively see it if you were lucky enough to like drill through one or you saw it in the field. But yeah, this is very much of an unknown. This is what some of the layered evaporite or syn salt, so the same age as the layered evaporite inclusions up here. This is from offshore Brazil. And then we have the North Sea over on the bottom left, the zechstein salt. You see little stringers of carbonite, anhydrite, and gypsum. And then here we have witchelina diapirs. So this is the neck or the base of the diapir. And you can see this beautiful recumbent fold sitting down here of the layered evaporite sequence. So this, you really see a very high degree of structural deformation within these layers. And then lastly, or second to last, we have the post-salt. So this is the younger sediments that can be incorporated into salt. This is an example up top of a roof or a carapace. So if you have another salt body coming, either in the computer or out, or maybe coming off from the side, those salt bodies will come together and coalesce, and you'll actually get these bits of stratigraphy all caught up and entrained in the salt body. Likewise, this is another image from the Gulf of Mexico down here. You can get a big salt canopy folding over onto itself, and you can get bits and pieces of sediments incorporated in the salt from that happening. So these are two different types of sutures, is what they call them. And then lastly, we also have igneous intrusions. So there's been some more recent work, and actually in the historic literature, where intrusions will preferentially choose diapirs to flow through or to come up instead of the sediments, just less dense. And then also you'll see down here in this picture, the volcanics flowed into an evaporator or potash horizon over here, forming a sill. So due to pressure, potentially temperature differences, things like that, it'll actually enable and allow volcanics to flow into salt bodies. So this is actually something I'm starting to kind of think more about and working on. I think this is going on in the Flinders. So yeah, more on that later. And then one of the last few things I want to talk about, I just wanted to bring this up because I've had lots of conversations with the author of this, is Trev Mount. He's had some really amazing observations at Arkapa diapir. And you can see here that his diapir is sitting right here, and the way that he's drawn it is not, it doesn't form how a typical diapir behaves. It is behaving the way that it's drawn more like a igneous intrusion. Like the rule of cross-cutting relationships is really being applied here. So this is something that I think, I mean, his image is beautiful. I find this to be really fascinating and find it very curious to what is going on here. So this is definitely something that still we're hoping to understand. And then the last thing that I wanted to show y'all before I go is just some new Aeromag data that was acquired over a diapir. So this is an exploration project currently going on right now. And you can see over here that this is the diapir sitting over onto the left-hand side in this pink color. And you can kind of see how it changes in each of these different versions of it. But a lot of these are volcanics coming up through here. So one of the key questions is, okay, is this like a fault, and you have a fault from the rift, and you have some volcanics coming up along that rift fault, and it's preferentially choosing the diapir because the diapir is sitting over the rift, or are those bits and pieces really large blocks of you know, volcanics that have been incorporated into the salt? So anyways, the jury is still out on that, but I think I just wanted to show you this because I think this data is really beautiful. It's really high resolution for magnetic data. All right, so to wrap up today before I run out of time, so just some key messages from this talk is understanding the sedimentary response to diapirism, and that it's influenced by allocyclic, so salt tectonics are really regional patterns, but then also autocyclic processes. So that's more of the salt sediment interaction and things that are going on right up against a diapir. So as we move forward, it'll be really interesting to sort of understand the differences between those two and also when they come together. It's also really important from a resource perspective. And again, just emphasizing the cross-learning that can take place between petroleum, geothermal, hydrogen, and then also the mining industries. As we start to work in new salt basins across Australia, there should be an emphasis placed on the integration and collaboration between different people. I think when that happens, you can really have a lot of magic that happens within science. Also, there are so many interesting sedimentological features to discover that are related to salt in the Flinders Ranges. I think it's always really important for academic research and for exploration purposes to be open to new ideas and concepts, and to always be challenging each other with those concepts. And then, yeah, and then we need to make this discipline more accessible. Salt tectonics is full of jargon, and always just working to make it more accessible so more people can learn and understand it, incorporate it into their research. So I think that's all I have. Yeah, thank you very much.